The most probably interesting thing to people, interesting might be the wrong word, but the exam, it happened. Yay. The average is not as high as I'd want them to be, but it is what it is. So I added a 6% curve based upon, there was a couple questions, I think 3 questions the vast majority of people got wrong, so 2% per question, and that's how we end up with the 6% curve. Here's the distribution, and I'm going to kind of talk through how to interpret your grade, how to interpret your performance, what does the numbers mean, all that jazz, final grades, all that goodness, what do you do moving forward, all that. So, if you remember, at the beginning of, I mentioned this at the beginning of the semester, the way the grade of the class is broken down is 50% of your grade is effort-based. The quizzes, the discussions, the third one, the top pack questions. Basically, those are if you show up and you answer the things, you should get all of those points. If you do them, they're basically free points. You have access to any and all resources. So that's, if you just do it, you get all those points. So then the other 50% is the exam. And so that's important because when we look at these responses, that means, I mentioned this before, to get an A in the class, assuming you got the 50% that's just effort, you only need to get 80% or above on exams. So that's how I'm going to be kind of breaking this down. And 80% or above, to me, it shows mastery. 80% or above on the exam shows mastery. That means you understand what I believe you need to understand from physics, and that's an A, because an A, to me, represents mastery. So that's an 80% or above. If you're in this category, keep doing what you're doing. You're doing a great job. You're doing the right things. You keep doing what you're doing, you're going to do great and get an A in the end. A 60% or above, between a 60 and an 80, is then competency. It's kind of the word I'd maybe use for that. You're competent at it. It doesn't mean you necessarily mastered it. There's something maybe that's a little off somewhere, and the closer you are to an 80, the better you are. The closer you are to a 60, the more that's a little off. But if you're getting above a 60 on this exam, that does mean you understand physics. It doesn't mean that you understand, to get above a 60%, it doesn't mean you only understand 60% of what I taught. You understand more than 60% because there's so many steps involved and things you have to do together. So above a 60% on an exam to me represents you understand some physics. There's just some things that are a little off here and there, and those are going to vary from person to person. So I can't say, oh, it's this or this or this. But that's why it's a B. 60% to an 80% basically, again, corresponds to a B because that's competency. That shows you're competent at the material. You haven't met mastery yet. There's some voids and some holes. But the mistakes you're making aren't just due to random chance or silly mistakes. It's more than that. It's something is a little off. All right, between a 40% and a 60% then is the C category, and that means, okay, something more significant is off. It's not just like a few things here and there. Something is decently off, resulting in you making decent amount of mistakes, and therefore, that ends up in those categories. 46%. It does mean you understand physics. It means you understand some amount. It doesn't mean you understand nothing. That's one thing I want to point out here. As you go down this, it means that just more is off, but it doesn't mean you don't know anything. So 40 to 60% is like, okay, you do understand something, but there's some bigger holes, and those need to be kind of figured out. And then below the 40%, that's when we start to get into something's really off. Something significant is off, and your understanding of it. And so why that is going to be due to a variety of reasons. My big hope is that if you did all the problem sets and things like that, you aren't finding yourself in kind of this lower area. That's the easy solution. The easy solution to if you're in a lower area is just to practice more. It sounds stupid. It sounds boring. It sounds basic. But that is literally how do you get better at something? You practice it more. If you did all those things and you're still not doing well, then it's something in the practice is off. There's a statement, practice makes perfect. That's not true. Practice makes permanent. If you're practicing wrong, you're just going to get really good at doing it the wrong way. or you just might not be preparing in a way that matches the assessment. So I've mentioned this a few times. If you practice with the worked out solutions in front of you the whole time, not going to work. If you practice with someone guiding you through the entire time, not going to work, because that's the test. You don't have that. So at some point, you want to be practicing in a way that matches the assessment. And yeah, making certain you're practicing sufficiently. So moving forward, how often, it's always good to kind of get a sense of what is possible. So the reality is the final will replace the lowest test grade. So that is a thing. So that basically means your test one scored could not matter at all. If you do well on the final, it will replace it. Great, can completely override it. But just to kind of set realistic expectations. So if you're in the B category, it's totally possible to move up to A. That's actually not that big. It's obviously not a big gap. If you're in the C category, jumping up to the A is still possible, but you're going to have to change a lot of things, and it's going to require a good amount of hustle. If you are in the lower, less than a 40% on this, aiming all the way to an A is a very large jump, and we're 6 weeks in. So, we don't have as much time for you to... It is technically possible to go from a below a 40% and be able to achieve an A in this class, but it is very... a lot's going to have to change. And I say that I'm sure it's possible. I don't see it too often. So this is just based on my experience of working with students and seeing how much their grades shift over the semesters. I don't see it happen too often. It doesn't mean it's impossible. It just means that drastic changes would have to be made and things like that. But maybe jumping a couple grades. So again, from either the B to an A, C to the A, stuff like that. Generally, I don't see people going down. That's the only reason I see people going down is, again, if they stop doing what they're doing. And that generally only happens if some life emergency arises, and that sucks if that happens. And let me know if stuff like that comes up, and I'll do my best to work with you. As far as resources to take advantage of, reminder, so the help room, my office hours, all these things exist with the caveat that you do not want to come to any of these, my office hours or help room without having started the practice problems. Or if you do come in, that's fine, but you're going to be you just don't expect the person in those rooms, whether that's me or the learning assistant or another tutor, to be able to sit with you one-on-one and spend a dedicated amount of time kind of teaching the content. Because the reality is there's just several people and it's not possible generally. Unless you're the only person in the room, it is possible, it can happen, but it's unlikely. If you feel like you need that one-on-one attention, that is where private tutoring comes in, and that stuff is expensive and things like that, but it is very effective. Of course, receiving one-on-one help is very, very helpful and useful, but it is, there's a cost generally associated with it because it requires someone to give you their one-on-one attention who has expertise, and that expertise is... Anyway, so that is something I've heard of people taking advantage of, and that does generally result in the biggest gains. Obviously, if you're getting one-on-one help, that's the best way to improve in anything in life. But there's a cost issue with it. It's not a requirement, though. I'm not saying you need to do that. I'm just saying it is an option that people do take advantage of. The other free options are totally still worthwhile. They just generally require more hours on your own working on things, whereas one-on-one tutoring, your time can be used a bit more efficiently. Time is money. That's the reality in life. So, anywho, mention that realistic, just kind of things. So, one of the things that was curious to me is my studio class and lecture class. You all actually had very similar questions, but their average is a little more. The only and I don't mention this to say, how dare you not do as well as them. That's not what I'm saying. What I'm saying is the only variable on my end that's different is the time on the test and the number. So they had a longer time, 2 hours and 50 minutes. They had 24 questions and they had picked 2 out of 3 free responses. Why do they have more time? Because literally the class time is longer that's allocated to that. I don't choose how long classes are. Your all's test was 18 questions, multiple choice, pick 1 out of 2 free responses. So shorter test, but half the time. My thought is for this upcoming test to give you all even less multiple choice so that you can focus more on checking your work. So I'll go from maybe 18 to 16, just a little bit lower. Again, I don't want to make it so low. If I go all the way to 10, that means if you miss 1 question, you got a 90. 2 questions is an 8. So that's the balance. I want to make certain I'm giving you all time to accurately represent your understanding, and it's a balancing act between giving you enough questions so if you make silly mistakes, it doesn't kill your grade, but not so many questions that you don't have time to check it. So I'm going to try that. But to that end, I sent out a survey. So this survey is worth 2% extra credit. I do that because I want people to fill it out because it helps me improve and determine how things might have gone and all that jazz. So I'm just going to show you all this survey now, if you haven't opened it already. So this survey is open till the end of the week, just because I don't want to leave it open forever because at some point I got to reference it. So, more than that, actually. Look at that. You got so much time. You all got 2 weeks. All right. So, again, I'm just going to straight up open you the survey. It's very quick. It's basically all multiple choice. I don't care what you click. You still get the 2%. If you just go through this and click things randomly, fantastic. But if you want to give me feedback, try to give reasonable response. Like, the more useful feedback I get, the better I can do as a teacher, both for you and for future generations. So this first one is, have you taken physics before? This is just an interesting data point for me, to be able to, at some point, I haven't done this yet, but at some point actually look at my students' grades and see the correlation between these. It's nothing you can go back and change, but as I teach future courses, it might be helpful for me to say, again, reasonable expectations of how people do and all that jazz. All right, scale 1 to 10, how would you rate the difficulty of the kinematics portion? Scale 1 to 10, how would you rate the difficulty of the force portion? Scale 1 to 10, how would you rate the time given to complete each question? This is the one I'm really curious about. It didn't seem like on my end it was a rush, but maybe it was, and this will be a helpful way to do that. Obviously, infinite time is ideal. We don't have infinite time, so answer this question with the constraints in mind. Given the amount of time I'm able to give you all, and if you have more thoughts on that, there's a chance for a free response. So like, obviously infinite time. So try not to just answer like a 1 unless you really thought it was like absolutely awful. Generally, extremes are often not the case. It definitely was not more than enough time. Maybe it was for some people. But the hope is that I find somewhere in the middle and kind of where it's at. On the scale 1 to 10, how much of the problem sets did you go through? Again, this is helpful feedback for me. Looking at, did people actually do a lot of these? I have no idea. They're not graded. So I have no idea if people are actually doing this outside of the people that come to my office hours and I work with. And I did seem to, the people that I'm kind of familiar with, it did seem to be encouraging that people were working on things, did tend to do well. That's just from the handful of people that I have like in-person interactions with. So that's always encouraging to me. But this will be helpful. Scale 1 to 10, how prepared did you feel? So again, that's actually like comparing these two and seeing if they're matching. The idea is if people do a lot if this is high, then I expect this to be high. That's at least my hope. Again, be honest with these. I'm not going to look at individual students and like say, oh, that person didn't do it. No. I look at this as kind of a whole. I'm not looking at individual students. So honesty is going to give me the best feedback. Scale 1 to 10, how well aligned were the test questions to the teaching resources provided? And this last one is interesting. All of this is tied to you. Again, I'm not going to go back and look. I'm not going to go back and see this person said this. I mean, I don't know 90% of your names to begin with, so it's not going to really mean much. You don't need to worry about that. But this last one, I want to get as much candid feedback. So this links to a Google form, and the reason for that is this is anonymous. So this one isn't tied to you whatsoever. There is no way for me to figure out your responses unless you put your name in it. It doesn't ask for your name. So like unless you, for some reason, chose to write your name in this. I don't know why you would. So this is anonymous. You can just put whatever. You can put blah, like whatever. But if there's things that you think are useful, please put them here. I do scroll through these and read through these. It doesn't mean that I'll be able to incorporate all the feedback that's in here. There's just some things I cannot do. So like, if one of the things is like, make the test easier, like can't really, like, I have to teach certain things. I have to evaluate certain things. But if you're like, it'd be great to have this resource, or it'd be great if you did this differently, or things like that, things that are actually within my control, then I can do that. So you put that there, you answer it, it'll give you a code. The code is literally, I'll just straight up tell you, it's test 1. It'll tell you that's the code, put it in there. Again, This is all of this. I don't care what you put, you get the 2%. But the more honest you are with these things, the better I can do as a teacher, feedback, all that good stuff. So, anyway. All right. Then let me quickly go through the common questions. So I've already answered this, but it's going to be a common question. I've given your grader a deadline of not this Thursday, but next Thursday for the free response. As soon as I get those, give me 20. Within 24 hours, I will have the free response grades posted, meaning at the latest, your free response grades will be posted on the 28th. It could be sooner, but I'd rather over-deliver than under-deliver. I'd rather tell you all it's going to be on this date versus telling you all this date and it takes the grader longer. So, give a little bit of buffer for that. Once that's in, I'll update that. What's the other common question? Oh, next week, if you want to come by and look at your test, you're welcome to. I will show you the test. I'll show you the right answers, all that jazz. I do not currently have plans to post the test because making these things takes... So this exam, even though I had most of these questions already in advance, it still takes me 5 to 10 hours to prepare this exam because I have to make multiple versions and I double check things and I modify things. And so making a test from scratch generally takes 20 to 30 hours to make a good test. It sounds crazy, but to make a good test, one where every question, if you read it, you actually understand what it means. If you all encountered on the problem set, some of the questions had ambiguity and there's assumptions you have to make. Making it very clear and all that stuff takes a lot of time and effort. Making sure there's no typos. This test has to be perfect. I don't want you to, if there's a typo, that gets people flustered, and people get flustered, then other questions get affected, and it's just a hot mess. So anywho, all that to explain, that's why I generally don't post my exams after the fact, because once they're posted, I let people bring a 5x8 note card with whatever they want written on it. If the test is posted, someone can literally just print all those and have them and all that jazz. So you can see the problem there. But I say all this with the caveat that one of the things I'm going to test is I'm going to try putting my test into ChatGPT and see how good of a job it does making different versions of the exam that look completely different. And if it does a decent job at that, then I can just feed it my exam, spit out many versions and many different problems, and then I don't have to worry about this. And, ChatGPT makes your lives more efficient, right? Mine included. So I'm going to try that. No promises. But if that works, then I can post the exam with everything, which will really just be relevant for you all in the final. That's really where the stuff, you are going to see problems like this in the final. The final is cumulative, hence why it can replace your lowest test grade. Because if you don't know it now, but you know it then I'm a happy camper. All right. Questions? Oh, yeah, but if you come to office hours, I'll literally show you the answers. I'll show you all that because it won't go with you, and therefore it has no risk of ending up online or in some secret folder somewhere or whatever. If you have a question, I guarantee you 10 other people do. All right. Tomorrow, I have some people doing makeup, so I'm not going to talk about the questions on the test yet. But next week, I will talk about the most missed questions, and because again, so the most missed questions that I'm going to talk about next week, you can almost guarantee will be on the final. Because great, I didn't teach them well enough. I'm going to go ahead and teach them well enough, and then ask them again. And that's the idea. So I will go over those 3 questions or so that the vast majority of people missed, because clearly there are things that we need to talk about more. All right. So, great news. Test 2 tends to do better than Test 1. There's lots of reasons for that. Some of it is people just learn better learning strategies. Some of it is that the skills that you learn from the Physics 1 test transfer to the Physics 2 test. We're going to use the same variables and all that. Another reason is the first thing I'm about to teach you all, work and energy. It's scalars instead of vectors. In my opinion, this PowerPoint slide. So there's 3 topics we're going to cover on Test 2. And actually, the problem set's already posted on these. So it's 4 weeks, but 3 topics. Energy is the first one. We're going to spend a week and a half on energy. Momentum is the second one. We're going to spend a week and a half on that with a tiny bit of center of mass because they're related. Week and a half energy, week and a half momentum. And then the new thing I'm doing that I haven't taught this in a previous class is fluids. So these questions exist here. And the reason I'm doing fluids is every single one of you, if you're in the medical field, cares about fluids because the body's full of them. Blood pressure is the obvious thing. What the heck is pressure? And how does that vary in the system? And a lot of the problems I actually chose for fluids relate to medical applications, mentioning the heart and blood pressure. Some of these at some points no. But as time goes on, we have eyes. We have, where's the next one? This one's finding someone's density based on water. This one's about the blood and the heart, blood, whatever. And echo, this one I made myself, very proud of it. Echocardiac exam and how it does, whatever. Anyway, there's a handful in here because they're relevant for medical stuff. I hadn't done them before, but for you all, it made sense to do them. I haven't made the slides for these yet, but I have chosen the problems. Those then motivate the slides, which in turn make the quizzes, and woo. But we'll spend a week on that. We have 4 weeks, and it works out really, really nicely that after these 4 weeks is spring break. So we have this week, next week, the third week, the fourth week, then it's spring break, then our exam is the week following that. Which I personally like because that then gives a buffer between the last class where we finish fluids, and then you have 2 weeks until the exam, which, it's not fun to have to study over spring break, but at least it's better to have the option than not to have extra time. If you're not able to, it is what it is. You have the same amount of time you normally would. You'll still have that Tuesday as a review day and all that good stuff. But I do like that it gives you a little bit of extra buffer time between the last thing I cover and when the exam is. So, that'll all go great. So much fun. And yeah, this first section that we're going to do today, energy, is in my opinion the easiest thing we're going to cover the entire semester. Opinions may differ, but one of the major reasons for that is there's no vectors. It's no more. This one doesn't have x and y components. But then we get to momentum and we're back to vectors again. And then we go to fluids and there's no more vectors again. So most of this exam won't have vectors. 40% of it will, I guess. Still counts as most of it not, but all right. So energy. How much time can I spend on this first question? I don't think I can spend. But anyway, we're going to talk about what energy is, which is something that energy is really easy to do mathematically. But the more you think about energy, the less the harder it is to explain. So we'll see what I mean in a little bit. We're going to talk about work, kinetic energy, potential energy, all that good stuff, power, fun time. Let's see. Do I want to devote the time to this? Yeah, sure. Why not? It's a freebie. I am going to give you all 2 whole minutes to type your definition of energy. What is energy? And just to make it interesting, whatever explanation you put, try to put it in wording that you could explain to an elementary school kid. That's how you know you have a mastery of a concept. If you can explain it to an elementary school kid, 3rd, 4th, 5th grader, that means you understand it well. That's a good rule of life. A good rule of thumb for y'all for anything you learn, ever. And you can talk with people around you if you want as well and hear what they have to say. It's interesting, right? I'm interested in it. Maybe you're also interested. Ask the person next to you what they think. All right, about 10 more seconds. All right, in 5, 4, 3, 2, 1. Good job. All right, what is energy? Let's see if I get the response I got a lot of this morning. Ability to do work. Force that makes something move, that's going to be related to work. Force, that's going to be work. Amount of work, great. Heat transferred, good. That's one. Force, all right. Force, great. Okay, so what's really interesting here is if you look up the definition of energy, it is often defined as the ability to do work. And then the problem is if you look up the definition of work, it's how much energy is gained or lost from a system. And so if you see the problem, they're defined on each other, and you end up with a circle where energy is the ability to do work. Work is the ability to gain or lose energy. And what the hell is it? So great question. So the best answer I have found, I say the best answer, one that I think is kind of cool, interesting. So this is a quote by Feynman, and I don't know if it sounds fancy or not, but I like the wording of it. So Richard Feynman is a pretty famous physicist. He did some with black holes. But he says energy is the most, that's Stephen Hawking. Feynman, I have to look up what he did exactly, but he's pretty well known. Clearly not by me. But, I know his name is. Anyway, energy is the most abstract idea because it's a mathematical principle. It says that there's a quantity you can calculate, some number you can calculate, which does not change when something happens. It's not a description of a mechanism or anything concrete. It's just a strange fact that when you calculate this number for energy, and then nature does some stuff, and you calculate it at the end, they're the same. And so, long story short, this is kind of just what is energy. It's something if you calculate it, stuff happens, you calculate it again, it's the same number. So what is it? I don't know. Does this actually tell you what it is? No, but really this is how so one of the always interesting things in physics, I told you all, everything starts with observations of reality. And then we build equations from that and we go from there. So the observation of reality here is that these people literally calculated some value. Stuff happened, and they found when they calculated that value again, it's the same. That's how this is discovered. Is it real? I don't know. But it's a thing that happens. It's a thing that happens. If you calculate this, then stuff happens. You calculate it again, it's the same. So what does that all mean? I don't know. It's a really interesting philosophical thing. But that is my definition of energy. Energy is, let's see, I think I have it here. It can change form. So I'm not going to test you on these words or anything. It's something that can change form, something, and is it even real? Who knows? But you can calculate quantities. You can calculate this thing. It's calculated in different ways for different things. Kinetic energy, potential energy, thermal energy. They each get their own special little equation. And it turns out if you calculate all the energies you start with, and assuming no energy gets added or lost from the system, at the end, if you calculate it all again, the number is the same. And you add them all up, that number is the same. Great. And you can change it from one type to the other, and that's energy. It's one of those things that you've probably heard about. Everyone knows what the word energy, like you ask a kid, what does energy mean? Well, if you have energy, you can do a lot of things. Honestly, I find that to be a better definition than work because they end up cycling. But yeah, it's a weird thing. The more you think about it, the less it makes sense, but it's useful. So it's kind of nifty. It cannot be created or destroyed. There is a asterisk here, along with there's a set amount in the universe. There's a little asterisk there. And I'll talk about that in just a second. It's a scalar, which is a word you haven't seen probably in a while or heard of, because we haven't had scalars. Everything we've done is a vector, which had a direction and an amount, and you had to break into x and y components. This doesn't have x and y components. This is just a number. And what's really nice about this is it matches all the ways you expect about numbers. So because it's a scalar, positive and negative don't mean which way the energy is going. There is no direction to energy. If I said the energy is going to the right, what does that mean? Doesn't mean anything. It's nonsense. It doesn't mean anything. But what it does mean is that 10 joules is a bigger number than negative 10 joules. So negatives actually mean an amount here. If a negative number is a small number when it comes to scalars, a positive number is a big number. Well, relatively. So that's the takeaway here. Positives and negatives do not mean left, right. they mean what you wanted them to mean the entire class. Negative 10 is smaller than positive 10. Joules is the unit for energy. Spoiler alert. It's going to come up a bunch. It's named after a guy with joules. Shocking, right? All right. Energy cannot be created or destroyed. Set amount in the universe. Yes and no. You all actually know kind of this. What is the most famous, I say, my opinion, what's probably the most famous and most well-known physics equation that if ever you see a shirt with physics on it, it's probably printed on it? Yeah. E equals mc squared. So fun fact, E is energy, m is mass, c is the speed of light. So this equation tells you that you can convert mass into energy and you can convert energy into mass. So that's kind of the thing if you haven't learned that before. It's a really weird thing. So you can destroy mass and it turns into energy. And you can destroy energy and it turns into mass. And how you do that, the easiest one is the mass. It's how the sun works. If you take the mass of a hydrogen atom and the mass of another hydrogen atom and you add those numbers together, it's a number. Great. If you combine two hydrogen atoms together, it turns into a helium atom. That's how the sun works. Two hydrogens turn into a helium. If you take the mass of the helium atom, it's smaller than the mass of two hydrogen atoms. Where did the mass go? Energy. So that's an easy example. That's how the sun gets its energy. Fission is the same way. When you break a thing, same thing. The mass you started with, the particles that come from it, they have a smaller mass if you added it all together. Where to go? Energy. Why? Great question. Takes a lot of time to explain in information I don't know. So, two things I can't really help you with. Time and energy. Anyway, so there you go. E equals mc squared. Don't need to know it, but it's a fun fact. I am not going to ask you a question like this in the exam. I'm not going to give you a question. Can energy be created or destroyed? No. This is stupid. No. But it's a fun fact, nonetheless. All right. This next slide is the most important slide in the entire PowerPoint. It's so important it shows up 5 times, I think. I literally just copy and pasted this slide like 4 different times. This is how you do energy problems. Force problems, sum of forces equals MA. Use that again and again and again and again and again. Energy problems, this is how you're going to solve every single energy problem is this. So I'm going to talk about it now. I'll talk about it again. I'll keep talking about it. It's really straightforward. The energy I start with plus the work done equals the energy I end with. So I'm going to teach you all that there's various equations for energy. We're going to eventually learn that there's 3 types that we're going to learn in this class. There's way more than 3 types. We're only going to work with 3 types in this class. Kinetic. So if you add up your kinetic energy initial, your potential energy due to gravity initial, your spring due to gravity initial, that's all your initial. Then you add work. That's going to equal your kinetic energy at the end plus potential energy at the end. Look, there's more types of energy than this, but these are the only 3 in this class. It just says the energy, all add up everything I start with, plus work equals the energy I end with. And I really hope I can explain work better than I was taught it. Work is one of those phrases that gets used all jargony, and it got used in some of your things, and it's great, and it's useful, and we're going to calculate it. Work is literally, are you adding energy to a system or taking away energy? That's it. So it's easy with numbers. Say I start with 10 joules. And I end with 15 joules. How much work was done?
5.
It's 5. It's positive 5. I added 5 joules of energy. So this is literally just saying I added 5. Work is just how much energy got added. If you add 5 joules, you gained energy. How do you add energy? By pushing something. We're going to find by pushing things and by applying force. That's one of the ways. All right, where's the opposite? What if instead I started with 10 joules and I ended with 5 joules? What was the work done? Negative 5. What does that mean? It means I lost 5 joules. That's all work is. Positive work means I gained energy. Negative work means I lost energy. Where did the energy go? Something outside the thing. Friction, or it's something outside the system. So, what you start with plus what you gain equals what you end with. If your bank account starts with $10 and you deposit $5, you now have $15. Where did the money come from? Something outside your bank account. Alternative, I started with $10, I took $5 out, I have $5 left in my bank account. Where did the money go? Outside your bank account, somewhere outside it. Ta-da, system and environment. Bank account and environment. That's my little analogy I made up right now. All right, so I mentioned system and environment. Again, I'm not going to test you on these words, but they are words that come into play, and you're doing this whether you realize it or not. We have the system. Think of that like your bank account. Then you have the environment, which is everything outside your bank account. So we have to pick what our system is. What are we actually tracking? What are we actually keeping track of? Environment is literally everything outside it. So maybe your system is a car, and the environment is the road, the air, literally everything around it. Maybe we drop a eraser. That's my system. I say, how does the energy change of this eraser? How much work is done on it? That's my system. What's the environment? Literally everything else. Great. I'm never going to ask you a question, what's the system and what's the environment? But you will be making this decision when you solve problems, whether you realize it or not. You are choosing something to look at and ignoring everything else. You did it with free body diagrams. You picked something to look at, you ignored everything else. Same idea. Again, the system is not isolated from the environment. It is literally impossible to remove something from reality. Like, you can never fully isolate anything from everything. You can do a pretty decent job. You could put it in a vacuum. You can move it really far away from the earth. But even then, there's always light and radiation and things that you never remove everything, ever. It's impossible. There's always something that's interacting with it. Great. Vocab words that I don't need you to know, but you'll secretly be using. And you'll hear them in various, if you ever hear any physics stuff, you'll see these words. All right, work. There is actually many ways to add energy to a system. We're just going to use this definition. We're just going to talk about mechanical energy in this class. We're not going to deal with thermal energy at all. That's its own topic. So we're only going to talk about how you change the mechanical energy of a system, i.e. in this case, make it go faster or slower. How do you make something go faster or slower? You already know this. How do I make that eraser go? I don't have anything. Oh, I have a baseball. How do I make this baseball go faster or slower? What do I do to it? Oh, wow, look, there it is. You apply a force to it. Work is the force times however far it's traveling during that times cosine of the angle. The force part's going to make sense. So, like we just said, you need to apply a force to add energy or take away. Delta X is basically over what distance is that force being applied. And then this angle is the trickiest thing of the whole bunch. And it's nothing super tricky. It's literally just the angle between the force and the direction you're going. So, but it is something that people often forget. So if you're moving to the right and your force is up to the right, the angle is the angle between those two things. The angle is the angle between F and delta X. Between F and delta X. The direction you're going and the force applied. And we'll talk about this and give a bunch of examples, and it'll be great. But really straightforward equation. Take the force, multiply it by how far you went, multiply it by cosine of the angle between them. Done. Every slide after this is just trying to understand this conceptually. The math is very simple, though. The unit's joules, because it's how much energy you add or take away. Every single unit in this entire PowerPoint is kinetic energy, joules. Work, joules. Potential energy, joules. Everything's joules. The only exception is when we get to power, because power is how much joules per second. But we'll get to that when we get to that. Joules is the unit for energy. It's all energy. It just looks different. All right. Now, we've already mentioned this, work can be positive or negative. Are you adding energy or are you taking away energy? Positive if you're adding energy, negative if you're taking it away. So, how do you find the sign of it? How do you figure out whether it's positive or negative? It's from that angle. If you all remember the equation, well, I say remember, I'll just put it right here. It's the absolute value of F. That's going to be positive. It's the absolute value of the displacement. That's going to be positive. So literally the only thing that's not absolute value is cosine of the angle. How do you determine the angle? If you're pushing in the direction it's going, it's positive. It's 0 in that case. So here's my force. Here's my delta x. If two things line up with each other, what's the angle between them? 0. Theta is 0. They line up with each other. Cosine of 0, it's very tempting to say it's 0. Cosine of 0, if you plug it in your calculator, is positive 1. Great. It's positive. Work is positive. If you push something in the direction it's going, you're going to gain energy. You're going to go faster. No surprises there. You gain energy if you push something gains energy if you push it in the direction it's going. If you push something opposite the way it's going, will it speed up or slow down? Slow down. Am I gaining energy or losing energy? Losing. How do we see that in the math? What's the angle between two things? Opposite direction, anti-parallel. 180. You plug in cosine of 180. You get -1. Your work will be negative. You lost energy. You made things slow down. By definition, that's less energy. Matches what you'd want it to be. So, this is just showing you the math matches the logic. The math matches the concept. If you can do the math, great, but if you know the concept, you're less likely to make a silly mistake. So, there you go. And look, I even had the answers here the whole time. How exciting. But yeah, that's kind of the idea behind work. Now, what if it's not perfectly parallel? Or what if it's not perfectly anti-parallel? What's up with this whole cosine thing in that case? So we are going to see how we feel about vectors again. I know I mentioned we're not going to use them for energy. Pretty much we're not going to use them. And this slide is to show you why. So I have a vector A that points to the right. I have a vector B that points up to the right. If I want to find the part of B that is parallel to A, I want to find the part of B, the component of B. So you can turn B into a triangle. There's my triangle. This part's B perpendicular. This part is B parallel. If I want to find the part of B that's parallel to A, how do you do it? Is it B times sine of theta, B times cosine of theta, B times tangent of theta, or is it just the value of B? All right, we'll go like 15 more seconds. All right, in 5, 4, 3, 2, 1. All right, so you want to find the part of B that's parallel. That's the adjacent side. This is the opposite side. That's the hypotenuse. So we're going to use cosine equals adjacent over hypotenuse, and you know it's this. Great. Why did I even mention this? Why did I mention this? If I wanted to multiply A times the parallel part of B, so if I just wanted to write this out, I want to do A times the magnitude of A times the parallel part of B. What would that equal? AB cosine theta. This is where the equation comes from. Fx cosine theta. All you are literally doing is you're taking the part of F that's parallel to R. You're finding the part of F that points in the direction you're going or points anti-parallel, and you're multiplying it. That's all this cosine theta is doing, is it says find the part of the force that lines up with it, with the direction you're going. then multiply them. So you don't need to know this, but it's where the equation comes from. If you all look at this, F times delta X times cosine of theta, and if I just rearrange this, it's literally saying, hey, I have some force, multiply it and find the component of it that lines up with delta X. If I push in the direction you're going, you get faster. If I push opposite of that, you get slower. If I push any other direction, nothing happens. So, great. There's that. Now we're going to get into, does this angle make sense and all that jazz. And I need to mark correct answers. Yay. All right. I hold a 10 kilogram weight above my head for 5 minutes. How much work do my, and I'm going to even change this a bit, do my arms do? We're going to look at the whole arms. And another way of wording this is how much energy did I add or take from the weight? Those two questions are identical. How much work did my arms do? Or if you want to rephrase the question, how much energy did the weight gain or lose? That's all work is how much energy it gains or lose. And the arms are the only thing affecting in this case. Technically gravity is as well, but the answer is the same. Oh, I'll even put the equation for you all. You should be able to do this math in your head. All right, we'll go 10 more seconds. All right, in 5, 4, 2, 1. All right, so we're going to go through this whole equation. If I am holding this thing up, am I applying a force to it? I'm holding a baseball up. Am I applying a force to it? Yeah, if I'm not applying a force to it, it should fall. Gravity should pull it down. Great, there is a force. That force is upwards. Fantastic. Next term, delta x. How much did it move? None. Delta x is 0. Who cares about the rest? It's done. 0 times anything is 0. So, this is a classic question. Like this question always gets asked in every single physics class. Yes, your arm gets tired. And why your arm gets tired is kind of complex. It's because there is stuff inside your arm that's doing things. Your body is having to do energy to make your arm stay in that motion. But I didn't ask about inside your arm. I asked, is this weight gaining or losing energy? Are you doing work to the weight? And so basically I could have phrased this as, hey, a water bottle sitting on a desk. How much work is the desk doing on the water bottle? None. It's not gaining any energy. I don't care how long it sits on that desk. It's not going to gain any energy. That's what work is. Is this thing causing the object to gain or lose energy? In this case, no. I don't care how long you hold it for. You're not making that thing gain any energy. It's not storing up magical energy from you holding it, at least not in physics terms. You'd have to go to the supernatural if you want to believe anything in that category. So, no, there you go. If it doesn't move, no energy gained or lost. Now, I say this with a caveat. You could technically make the argument that you're heating it up as you're holding it, and that's its own type of energy that we are not going to cover in this class. We are not going to cover heating things up. That's called heat. and we just aren't covering that in this class. So yes, technically it is getting warmer. So technically you are gaining it, causing it to gain it, but we're going to ignore that in this class. All right, great. Next one. A 2 kilogram box starts at a height of 3 meters and falls to the ground. How much work does gravity do? We always say, whenever I ask how much work something does, we have to specify a force, or we have to say all the forces together. So in this case, I'm only asking you what's the work that the force of gravity does. Do not ignore air resistance. Doesn't matter, actually, in this problem. You only care about gravity. Even if there's air resistance, we don't care about the work done by air resistance. We only care about the work done by gravity. Oh, and there's positives and negatives here, so make certain you're careful with those, because that's going to come up in the next few questions. Make sure you draw some arrows. What is the direction of the force? What is the direction it's moving? What's the angle between those two things? All right, we'll go like 15 more seconds. All right, we'll close it out in 5, 4, 3, 2, 1. Oop. All right, so work. Force times however far you move times cosine of theta. So we just say, all right, what's doing the work? Gravity. That's the one I'm asking about. So I put that there. And immediately I'm going to go ahead and draw some arrows because we do care about the direction. Gravity is down. Hopefully we're all cool with that. And which way is it going? Is it going up or down? It's going down. Great. So we draw the little arrow right here. We need that to figure out the angle between them. So then the equation for the force of gravity is m times g. And this is one of those, again, do I put g as negative 9.8 or positive 9.8? Who cares? It's absolute value. Gets rid of it regardless. Whether it's positive or negative, there's literally only a single term that can be positive or negative, and it's the cosine of the angle. Everything else is absolute value. So I just put in the numbers. So 2 times 9.8 times 3. And then you have to make a judgment call. What's the angle? The angle between two things that are parallel is 0. And you plug all that in and you get 58.8. And it's positive. Because does gravity make it go faster or slower in this case? Faster. It's falling. It gets faster and faster and faster. Gravity is making it gain energy. It's going faster because of gravity. So gravity is doing positive work. It all lines up. The concept, the math, everything comes together. And we find that gravity added 58.8 joules of energy to it by pulling it downwards. Great. Okay. We're going to do like every variation, not quite every variation, but almost every like a lot of variations on this. Ooh, good, different answers. All right, chance for redemption. A 2 kilogram box starts at the ground and gets You know, it says lifted. You could say tossed 3 meters upwards, whatever. It goes 3 meters up. I don't care how it does it. Doesn't matter. How much work does gravity do in this case? And there's only 3 choices. So there's no, you don't need to repeat the math. You basically need to make a judgment call. Is it doing positive work, negative work, or no work? You don't need to replug things in the calculator. It will either be 0 or 58.8. You need to decide whether it's positive, negative, or 0. We're specifically saying how much work does gravity do. It matters what force you look at. All right, we'll go 10 more seconds. In 5, 4, 3, 2, 1. Boop. All right. So, you know, it's the exact same equation. Work equals force times delta x times cosine of theta. It's still force of gravity. It's still delta x. Great. So, which way is gravity point? Still points down. Nothing's changed there. Which way am I moving? Up. So what's the angle between them? 180. So the math all ends up exactly the same. You still have m times g times your delta x, but now cosine of 180 is -1. Let's think through the logic here. Does gravity make it go faster or slower? Slower. On the way up, it's making it go slower. It's making it lose energy. Work is negative. Positive work, gain energy, go faster. Negative work, lose energy, go slower. That's the idea. Really nice and straightforward. Within this context of faster or slower. Great. Let's see how we did here. If you didn't get this one, that's all right. There's one more chance for redemption. We have done up. We have done down. We've done up. We've done down. The last one, a 2 kilogram block starts at the ground, and I push it to the right 3 meters. How much work does gravity do? Still looking at only gravity. I don't care why it's moving to the right. I am saying what's the work that gravity does. You have to choose what force you look at. All right, we'll go 15 more seconds. All right, and 5, 4, 3, 2, 1. Yeah, I'm gonna close it up. All right. So, same exact equation. Had so much fun writing it the first few times. We'll write it again. Oh, it's still the force of gravity, which is m times g. It's still delta x. Again, it's only gravity again and again and again because I asked you for gravity. If it was something else, it'd be something else. Great. Which way is gravity? Down. Great. Which way am I moving? Right. What's the angle between those? 90. If you all plug in cosine of 90 in a calculator, it's 0. So mg delta x times 0 equals 0 joules. Forgot the unit here. Terrible of me. Shame on me. Yeah, and again, think through the logic. Is gravity making it gain energy, lose energy, or not doing either of those things? It's not. Gravity does not make things go faster or slower, left, right. It's just not how it works. X and Y are independent, all that jazz. If my delta X was at an angle, that's for that cosine of the angle, and you'd find the part of it that does make inclined planes and all that good stuff. But in this case, I picked the extremes. I picked straight up, down. I picked left, right. There we go. Someone picked D. That's wild. Yeah, you can expect some problem like this in the test. Really easy questions. These are the conceptual questions. Do you understand the idea? You can prove it with math. You can do it with the concept. Everything works out great. And then, yeah, so what's doing the work? If there's a component of force, if there's a force and at least a piece of that force lines up with the direction you're going, as long as it's not perpendicular, as long as the force isn't perpendicular, it's going to make it go faster or slower. If you had like this, the lowest incline, like the most gentle inclined plane you could possibly imagine, like that, it's too hard to draw, but imagine that, and I had this, then gravity is down, but this angle is not 90 degrees. So gravity does make it speed up down that. And so it is doing work. And that's the cosine of the angle and you know, all that jazz. Whatever is causing the force is doing the work. So you have to choose. Is it the friction force? Is it gravity? Is it applied force? You can even do the net work, which just means get the net force and find the work done. Whatever, you got to pick something. Either everything together or individual pieces. As I've said, positive work, energy is added. Negative work, energy is taken away. You might have to draw a free body diagram to figure out the forces that are happening. That's still a useful skill that doesn't go away. The nice thing is, well, for good or for bad, the skills that you develop for test 1 are going to continue to show up. So all that time and energy you spent for test 1, it still gets used. All of physics builds. Every single equation basically moving forward is going to involve positions and velocities and accelerations. Everything's just going to be some combination of variables you've already learned. There isn't, I don't think there's any new variables at all. Everything comes down to position, velocity, acceleration, and time. Everything can be found from those. Oh, and mass. All right, great. All right, here you go. An object's falling through the air. What's doing work on it? Is air doing work on it? Is gravity doing work on it? Is no work done? Is the object doing work to itself? All right, we'll go 10 more seconds. Again, this is one of those, you know it or you don't. All right, in 5, 4, 3, 2, 1. All right, so we draw a free body diagram. What forces are acting on it? You have gravity. It says through the air, so we're going to go ahead and put force of air. What's the right answer? I don't care. Both of these are good. Either one's great. They're both doing work on it. Gravity is making it speed up. Gravity is doing positive work because it's falling downwards. Air resistance is doing negative work. That's just if you had to calculate this because the angles between them and, you know, all that good stuff. So either of these is right. Obviously, I wouldn't ask a question like this in the exam that has 2 right answers. So, but it's just to remind you, either one can do work. The net work would be the work of both of these added together. Or the work of these, you'd get the net force and do the work that way. And it works out the same. Either way you do it. If you want the net work, you can either find the work of gravity and the work of air and add them together. Or you can get the forces, add those together and do it. And it all works out the same. So, here's an example of that. And I really, really like this problem because it segues us from the last test into this. To do part A, you have to use skills from the last test, which I kind of like. Shows everything builds. Calculate the work done on a 1,500 kilogram elevator car by its cable to lift it 40 meters at a constant speed, assuming friction averages 100 newtons. What is the work done on the elevator car by the gravitational force? What's the total work done? Anytime you all see the word forces in a problem, there's always something you should do. You should draw a free body diagram. Yep, go ahead and do it. Even if you don't know why you need to do it, just trust me, you need to do it. It's one of those nice rules. Even if you don't know why, do it and figure out why later. All right, great. There's my elevator. You all tell me, what forces are affecting it? Gravity. Which way is that? Fantastic. Great. What else? Friction. Which way is that going to be? Which way is it moving? So we can draw that a little bit off to the side because we will reference that. It's not a force. We just put it to the side because we do use it. If you're moving up, which way is friction? Down. Friction is always opposite the way you're going. Always in our class. And that's pretty much always true. Great. According to this, my thing should be accelerating downwards. Why isn't it? Yep, there's a force tension pointed up. Great. Now that we've drawn that, let's actually then start to solve this problem. Even though I haven't seen yet why we need it, we will. Mass is 1,500 kilograms. My delta X is 40 meters. So again, we're still using the same skills. What's given, what's missing, all that good stuff. Force of friction is 100 newtons. There is one more given here that is extremely important, and it's in a key phrase that if you ever see this phrase, you should recognize this as a given. Yeah, acceleration is 0. Anytime you all see constant speed, that's an important flag. Every single problem where I've ever told you constant speed, you basically had to take that into account. That's just one of those. It's in words, but it's really important. It tells you it's not getting faster or slower. Fantastic. We are solving for the work done by something in particular, one of these forces. I'm going to give you 30 seconds or so. The work done by which force, or is it all the forces together? Make that judgment call in your head. And then I'll show you what the answer is. All right. We are finding the work done by its cable to lift it. The work done by the cable. Which the work done by the cable? The work done by tension. So I just put work tension. If it was work gravity, I'd put work with a little g next to it. If it was work due to friction, I'd put a little f next to it. And so that's what we're solving for. How do we solve that? Well, the work equation will be the force due to tension times how far it's going times cosine of the angle between them. That's the only equation for work that you currently have, so that's the one we're going to use. And then immediately we say, I don't know what the force of tension is. If only we could find the forces, blah, 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 Newton's second law. Anytime you need to find a force, I'm going to let you all see if you remember. I could have given you this problem on a test. Hey, here's an elevator going up. Find the force of tension. Totally could have asked this problem on the last test. See if you can think about how you would solve that. Give you 30 seconds. Anytime we're working with forces, it's always the same equation. There's only really one equation to even think about when it comes to forces. The sum of forces equals ma. That's always the one. And look, it's got A. Good thing we identify what A is, because we're going to need it. So the sum of the forces, we have force tension. That's positive, because it's going up. We have force of friction. That's negative, because it's going down. we have the force of gravity that's negative because it's going down, times m times a, and we're doing this just in the y direction, so I'll put little y's here. It's good to remember x and y, keep them separated, all that good stuff. We don't care about the x, there's nothing going on there. So, long story short, the force of tension is going to equal the force of friction plus the force due to gravity. And just to write that out explicitly, the force of friction plus m times g. Force of gravity is m times g. And there you go. Now we have that. We can find that. Then we can plug it into the other equation. And life is good, right? So much fun. So that is, finding this force. Totally could have asked that in the last test. It's not a new skill. What's going to be new is just chucking it in the equation. So, great. The force of tension is going to equal 100 plus 1500 times 9.8. I don't know what that equals. I think it's like 14,000. I think that's what I remember from this morning. But I don't remember. That's why I'm going to use a calculator. Yeah, 14,800. I did not do that in my head. Never think I do any math in my head. That's how you make mistakes. Great. And then we're just going to chuck it in this equation up here. So the work due to tension is going to be the force due to tension, which is 14,800. It's already absolute value, so whatever. The absolute value of 40, also already that. And cosine of the angle, I'll give you all 20 seconds. What's the angle? Don't say it out loud, give people a chance. What is the angle between the force of tension and the direction of motion? All right, now you can shout out loud. What is it? What's the angle between the force of tension and the direction you're going? 0. It's a positive 1 because this tension, if there wasn't gravity, would make it go faster in the direction it's going. Great. You plug all that in and you'll get 592,000 joules. That is how much energy the force of tension is contributing. It's trying to add that much energy to the system. But there's stuff counteracting it. So part B says, find the force due to gravity. Find the work due to gravity. Really, really simple. So part A was the hard part, and hard part is a relative term. I wouldn't consider this too bad. Part B says, find the work done by gravity. So the work done by gravity is just going to be the force due to gravity times the direction it's going, or how much it's traveled, times the angle between the two. So the work due to gravity is going to be m times g times the amount you went times cosine of the angle. And yet again, I'm going to let you make that judgment call. Give you a second. Mass is 1500. G is 9.8. Delta x is still 40. And then I pause for a few moments so you could actually think about what the heck the angle is going to be. It's great practice. All right, gravity's down, I'm moving up. What's the angle between those? 180. It's negative. Gravity's trying to slow this thing down. It's going upwards, gravity's slowing it down. You plug in the numbers, and you will get negative. It will spit out a negative because of the cosine of 180. Yay! And the last one, I didn't put the answer to. The last one says, we'll do it in big decisions. Orange. It asks for the net work. The work done by all the forces together. So to find the net work, we're going to do the net force times delta x times cosine of theta. And this one's really, really boring. If my acceleration is 0, what's my net force? Yeah, it's just 0. F net equals 0. Because A is 0. If your acceleration is 0, F net equals ma. So the elevator, long story short, is gaining no energy. It's not getting faster or slower. We knew that from the very beginning. The very beginning of the problem, we said it's moving at a constant speed. It's not getting faster, it's not getting slower, therefore it's not getting energy in this context. So, yay. Okay, I'm just going to show you all this slide, and then we'll kick off with it next class. The next thing I'll teach you all is power. Power is literally work divided by time. How much energy are you gaining every second? This is what your chart, if you multiply power times time, you get work, and that's how you get charged for your electric bill. That's kilowatt hours. We'll talk about that next class, even though you don't need it. Great. And then we'll talk about types of energy, and it's the farther we get in this PowerPoint, the easier it gets, as weird as that sounds. You'll see what I mean. The more it's all going to start to come together. Work is done. We'll do power. We'll talk about the types of energy next class. And then next Tuesday, we'll just do a bunch of problems. Fun time. See y'all. If you have questions, I'm here.